All right, this is going to be our walkthrough for the homework assignment titled L'Hopital's Rule. So for each of these problems, we're going to use L'Hopital's rule to evaluate the limit if it is possible to do so. So in order to use L'Hopital's rule, we first need to check and make sure it's one of the nice indeterminate forms that we can use L'Hopital's rule for. So 0 over 0 or some sort of infinity over infinity. But we're always going to check to make sure it's in that form, because if we try to use L'Hopital's rule and it's not in one of those forms, we're going to end up with a horribly, horribly wrong answer, and you're going to be really upset with yourself on the test for not checking to see if it was indeterminate. So if I plug in 3 to this, just to check, I end up with 6 minus 6, which is 0, over 9 minus 9, which is 0, which means that I can use L'Hopital's rule. Now on the AP test, what they're going to want you to do is they're going to want you to write out that the limit as x approaches 3 of 2x minus 6 is 0, and that the limit as x approaches 3 of x squared minus 9 is also equal to 0, right? And then you can use L'Hopital's rule from there to then say that this is equal to the limit as x approaches 3 of the derivative of 2x minus 6, which is just 2, over the derivative of x squared minus 9, which is just 2x. And then we'll plug in the 3 now, which gives us 2 over 6, or 1/3. So keep in mind that this is something they want you to do on the AP test. I'd like you to get used to doing that. So I'm going to ask you to do that as well for the problems on the test. All right, so for this one, we'll check the limit in the numerator. Right? The limit as x approaches 3 of, that's not a very good 3, of root x plus 1 minus 2 is equal to 0, right? Because that's the square root of 4 minus 2. And we know that the limit as x approaches 3 of x minus 3 is also equal to 0. So using L'Hopital's rule, we should be able to get the limit as x approaches 3 of the derivative of the numerator. Well, the derivative of that is just 1 over 2 root x plus 1, right? Because the minus 2 goes away. And then divided by the derivative of x minus 3, which is just 1. We should now be able to just plug in 3 to this. 1 over 2 times the square root of 3 plus 1, which is 1 over 2 times 2, so 1 over 4. For our next one here, the limit as x approaches infinity of this, we should be able to note that the limit as x approaches infinity of 5x squared minus 3x plus 1 is infinity, and that the limit as x approaches infinity of 3x squared minus 5 is also infinity, right? Because we're just having the squared terms dominate there, right? So infinity squared is infinity. And using L'Hopital's rule, we should see then that we can just take the derivative here. This should be the same as the limit as x approaches infinity of 10x minus 3 over 6x. Well, if we sit there and look at that, we could see that the limit as x approaches infinity of 10x minus 3 is infinity, and the limit as x approaches infinity of 6x is also infinity. So I could use a second application of L'Hopital's rule to just turn this into a limit as x approaches infinity of 10 over 6, which is just 5/3. And of course, if this was a multiple choice question on the AP test, you don't need to write out all that work, but the College Board wants you to write out the separate limits for L'Hopital's rule each time. All right, for this next one, we have a limit as x approaches 2 of x cubed minus x minus 2 over x minus 2. So this is one in which I am urging you to be careful with using L'Hopital's rule. Because if I plug in 2 to this, right, I get 8 minus 2 over 2 minus 2. Well, that's 4 over 0. 4 over 0 is not indeterminate. This limit cannot be evaluated using L'Hopital's rule. In fact, it can't really be evaluated at all. 4 over 0 is undefined, so this limit does not exist. For number 5 here, we're just going to check real quick to make sure it's 0 over 0. So the limit as x approaches 0 of root 4 minus x squared minus 2. Well, 4 minus x squared, if x is 0, should just be 4, right? So square root of 4 is 2. 2 minus 2 is 0. And of course, the limit as x approaches 0 of x is just 0. So we'll use L'Hopital's rule. And again, they do want you to write out that you're using L'Hopital's rule. L'Hopital's rule says this should be the same as the limit as x approaches 0 of the derivative of the numerator, which is 1 over 2 root 4 minus x squared, times the derivative of 4 minus x squared, which is negative 2x. And then the derivative of the minus 2 up there just goes away. And then all over the derivative of x, which is just 1. And so now we can just evaluate this when x is equal to 0. We end up with 0 over 2 times the square root of 4, all over 1. I don't need to write that. That just comes out to be 0. It's no longer indeterminate. And the value of this limit is 0. All right, for our next one here, we've got e to the x minus 1 minus x. Well, over x. And so first thing we'll do is check to make sure this is actually 0 over 0. So we'll do a limit as x approaches 0 of e to the x minus, e to the x minus 1 minus x. Well, e to the 0 is 1, and then minus 1 minus 0, right, is just equal to 0. And of course, the limit as x approaches 0 of x is just 0 as well. So we'll use L'Hopital's rule to turn this into a limit as x approaches 0 of the derivative of e to the x is e to the x. If I distribute that in the numerator there, it's e to the x minus 1 plus x, right? So the derivative of the minus 1 is 0, and the derivative of the plus x is just plus 1. And then in the denominator, we've now got a 1, because the derivative of x is 1. We'll just evaluate this. E to the 0 plus 1. E to the 0 is 1, so 1 plus 1 gives us 2. For our next one here, we got sine 2x over sine 3x. I think we know right off the bat that both of those are going to equal 0 when you plug in 0, but we'll write it out because that's what the College Board wants us to do. And now we'll say that we're going to use L'Hopital's rule and say that this is a limit as x approaches 0 of the derivative of sine 2x. Using the chain rule, that's 2 cosine 2x. And the derivative of sine 3x, which using the chain rule is 3 cosine 3x. We'll just evaluate that at 0, so 2 cosine 0 over 3 cosine 0. Well, the cosine of 0 is 1, so that's just 2/3. Here we've got the limit as x approaches 0 of inverse sine of x over x. Well, what's the limit as x approaches 0 of inverse sine of x? Well, it's just 0, right? Because the sine of 0 is 0, so the inverse sine of 0 is also 0. And we know that the limit as x approaches 0 of x is also just 0. So we can rewrite this using L'Hopital's rule by taking the derivative of the top and the derivative of the bottom. This becomes the limit as x approaches 0 of the derivative of inverse sine, which is 1 over root 1 minus x squared, all over the derivative of x, which is just 1. We can now evaluate. This is 1 over root 1 minus 0 squared, all over 1, which just comes out to be 1 over 1, or 1. All right, here's another one that's going towards infinity. So we should note that the limit as x approaches infinity of 3x squared minus 2x plus 1 is infinity. and that the limit as x approaches infinity of 2x squared plus 3 is equal to infinity. And therefore, we can use L'Hopital's rule to make this a limit as x approaches infinity of the derivative of 3x squared minus 2x plus 1, which will be 6x minus 2, over the derivative of 2x squared plus 3, which is just 4x. Of course, because the limit as x approaches infinity of 6x minus 2 is still infinity, and the limit as x approaches infinity of 4x is still infinity, we can use L'Hopital's rule again to make this the limit as x approaches infinity of the derivative of 6x minus 2, which is 6, over the derivative of 4x, which is just 4. And reducing that, of course, is just going to give us 3 over 2. All right, for our next one here, that's another infinite one. We'll note that the limit as x approaches infinity of x squared plus 2x plus 1 is infinity, and that the limit as x approaches infinity of x minus 1 is also infinity. So we'll use L'Hopital's rule to get the limit as x approaches infinity of the derivative of x squared plus 2x plus 1 is 2x plus 2, and the derivative of x minus 1 is just 1. Well, when I plug infinity into that, I get infinity over 1, which is just infinity. So that one is infinity, or you could say that that limit does not exist. Either one would be acceptable. All right, for our next one here, x over root x squared plus 1. Now, this one is a weird little case here. We're gonna work through it using L'Hopital's rule and actually see that that doesn't end up working. And so you want to kind of get used to seeing, when you see one like this, you're going to recognize that it doesn't work. But we do see that we should be able to use L'Hopital's rule, right? The limit as x approaches infinity of x is infinity, and the limit as x approaches infinity of root x squared plus 1 is also infinity. So if I try to use L'Hopital's rule, we're going to end up with a limit as x approaches infinity of the derivative of x, which is just 1, and then the derivative of root x squared plus 1, which is 1 over 2 root x squared plus 1, times the derivative of the x squared plus 1, which is 2x. And we can see that these will cancel out, and this becomes a limit as x approaches infinity. If I take the 1 over a fraction, it's like taking the reciprocal. So we'll have root x squared plus 1 over x. Well, if I look at that, I already know that the limit as x approaches infinity of root x squared plus 1 is infinity, and the limit as x approaches infinity of x is infinity. So I can use L'Hopital's rule again. And you can probably imagine what's going to happen here now. We're going to have the limit as x approaches infinity of the derivative of root x squared plus 1, which we just did, which was x over root x squared plus 1, over the derivative of x, which is just 1, which that over 1 is unnecessary. We just end up right back at our original function. So this is going to end up giving us an infinite loop here. We're just going to keep going back and forth between our function and the reciprocal of our function. And so what we need to do is we need to remember back to our limits unit. Just because we have a new tool at our disposal doesn't mean that we have to forget everything that we used to do to find limits. So what we did previously with problems like this was we said, let's just say this is a limit as x approaches infinity of x over root x squared plus 1. I'm going to divide by a root x squared inside of here. If I divide by a root x squared in the numerator, we need to remember that root x squared is the same thing as the absolute value of x. And if x is greater than or equal to 0, then the absolute value of x is just equal to x by definition. And since we're approaching infinity, the absolute value of x is equal to x. So dividing by the square root of x squared is the same as dividing by absolute value of x, which is the same as dividing by x. And so this becomes a limit as x approaches infinity of 1 over the square root of 1 plus 1 over x squared when you simplify the inside of that radical. And if I evaluate this going towards infinity, right, then we should get 1 over the square root of 1 plus 1 over x squared. 1 over infinity would be 0. So we end up with an answer of 1. So again, there are a few cases in which L'Hopital's rule will fail. In that case, you need to find a different method to evaluate the limit. All right, for our next one here, natural log of x over x. As x approaches infinity, we can see that the limit as x approaches infinity of natural log x is infinity. And the limit as x approaches infinity of x is infinity. So we can use L'Hopital's rule. And we now actually have an algebraic way to solve these problems. Right? Previously, we just said, oh, which thing is increasing more rapidly? But now that we have an algebraic way to do it, we should use it. This should become a limit as x approaches infinity of the derivative of natural log, which is 1 over x, over 1. Well, that ends up being just a 1 over infinity, which is 0. Which is exactly what we would have assumed was happening because the numerator was increasing more rapidly than the denominator was. All right, for our next one here, we are looking at a limit as x approaches infinity of the natural log of x cubed, which is infinity, and a limit as x approaches infinity of x, which is also infinity. That indeterminate form allows us to use L'Hopital's rule, which gives us a limit as x approaches infinity of the derivative of natural log of x cubed, which is u cubed, so it'll be 3 natural log of x squared times the derivative of natural log of x, which is 1 over x, and then all over the derivative of x, which is just 1. And of course, I don't really need to write that over 1, so I'll get rid of that. And then I think we can see here that this is now the limit as x approaches infinity of 3 times the natural log of x squared is infinity. And we already knew, in fact, I'm not going to even bother to write it again. The limit as x approaches infinity of x is infinity. So we can use L'Hopital's rule a second time, which is now going to give us a limit as x approaches infinity of the derivative of 3u squared ought to be 6u, so 6 ln x, times the derivative of the ln x, which is 1 over x. And then we will do the derivative of the x, which is just an over 1, which again, that part's not necessary. So we'll get rid of that. And we can see that this is still equal to infinity over infinity, right? Because the limit as x approaches infinity of 6 ln x is infinity. And again, the limit as x approaches infinity of x is infinity. So now we take another application of L'Hopital's rule. And this time we end up with a limit as x approaches infinity of 6 times ln x's derivative is 6 over x. And then the derivative of x is just 1. Once again, we don't need that over 1. So we'll get rid of it. And this just becomes 6 over infinity. And 6 over infinity is, of course, 0. All right, for our next one here, we've got the limit as x approaches infinity of x squared over e to the 5x. So the limit as x approaches infinity of x squared is just infinity. And the limit as x approaches infinity of e to the 5x is infinity. And so we can use L'Hopital's rule to give us a limit as x approaches infinity of 2x over the derivative of e to the 5x, which is 5e to the 5x. And then that's still infinity over infinity, right? Because the limit as x approaches infinity of 2x is infinity, and the limit as x approaches infinity of 5e to the 5x is still infinity. So we'll use another application of L'Hopital's rule. Try and spell it correctly. Giving us a limit as x approaches infinity of 2 over, now it's 25e to the 5x. And now as we plug in infinity to that, we can see that we get 2 over infinity, which is, of course, again, just 0. All right, for our next one here, if we plug in our 0 into this, we end up with e to the 0, which is 1, right? So we have e to the 0 minus 1 over e to the 0. Well, that's just 1 minus 1 over 1, which is just 0. So again, be careful. Try to, always try to plug the number in first and see what you get, right? That's why we always check those limits first. This one just comes out to be a 0. We don't need to use L'Hopital's rule for this, right? No L'Hopital's rule. And don't use L'Hopital's rule, because if you try to, you'll end up getting a wrong answer. So make sure you always remember to check first. All right. Our next one here is cosine x minus 1 over e to the x minus 1. Let's check this and make sure it's 0 over 0. So the limit as x approaches 0 of cosine x minus 1. Well, that's just 1 minus 1, which is 0. So the numerator is 0. If the denominator is not 0, then we're done. Our answer is 0. But it looks like e to the 0 is 1, minus 0 minus 1 is 0. So it looks like this is going to be a L'Hopital's rule problem. So we will use L'Hopital's rule. We will take the derivative of the numerator and of the denominator. Derivative of cosine x is negative sine x. And the derivative of the denominator, the derivative of e to the x is e to the x. The derivative of minus x is minus 1. And the derivative of the minus 1 is 0, goes away. Now, we probably immediately see that if I plug in 0 to the numerator, I get 0. And also that if I plug in 0 to the denominator, I get 1 minus 1, which is 0. Which means we're going to need to do a second application of L'Hopital's rule. Right, that second application of L'Hopital's rule is going to give me a limit as x approaches 0. The derivative of sine is cosine, so the derivative of negative sine is negative cosine. And then the derivative of e to the x is just e to the x, and the minus 1 will go away. And so all we need to do is now plug in 0. We have negative cosine 0 over e to the 0. Cosine of 0 is 1, so that's negative 1 in the numerator. And e to the 0 is 1, so that's 1 in the denominator. And so we end up getting negative 1 as our answer. All right, here, number 17, we're looking at the limit as x approaches 0 of the natural log of the cosine of the sine of x all over x squared. So, first thing we'll do is check the numerator and the denominator. The limit as x approaches 0 of the natural log of the cosine of the sine of 0. Well, the sine of 0 is 0, so this is the natural log of the cosine of 0. Well, the cosine of 0 is 1, so that's the natural log of 1. Well, the natural log of 1 is 0. So our numerator is 0. And I think pretty obviously our denominator is also 0. So we'll use L'Hopital's rule, which is going to give us a limit as x approaches 0 of, well, let's see here, the natural log of the cosine of the sine of x. Well, that's natural log of u, right? So natural log of u should come out to be 1 over u. So 1 over cosine of sine of x. But then we need to multiply that by the derivative of the cosine of the sine of x. Well, the derivative of cosine of v is negative sine of v, so negative sine of sine x. And then we need to, again, multiply that by the derivative of the sine of x, which should just be the cosine of x. So that's our derivative of natural log of cosine of sine of x. And then, of course, we need to put that all over the derivative of x squared, which is 2x. So we've kind of got a little bit of a mess here. What we've really got is a limit as x approaches 0 of the negative sine of x times cosine of x over 2x cosine of sine of x, which is a pain. But what we might see, though, that might help us a little bit to rewrite this is we have negative sine of sine x and cosine of sine of x. So really that's like a sine over a cosine here. Right? Sine over cosine is tangent. So we should be able to then rewrite this, at least make our lives a little bit easier, as a limit as x approaches 0 of the negative tangent of sine of x, which is a little bit better, times the cosine of x all over 2x. Right? And then, of course, unfortunately, I think we can see here what's going to happen. The limit as x approaches 0 of the negative tangent of sine of x times cosine of x is the negative tangent of the sine of 0 times the cosine of 0, which is negative 1. Well, the sine of 0 is 0, so this is just negative, 2 negatives, so we'll cancel out the negatives, actually make it a positive, right? A negative here and a negative here cancels out. So that's just the tangent of 0, which is 0. And I've kind of run out of room here, so we'll go to a new page. We also can see that the denominator there, the limit as x approaches 0 of 2x is also 0, which means we're going to use L'Hopital's rule again. And so now we're taking the derivative of the limit that we had was negative tangent of sine of x times cosine x all over 2x. So using L'Hopital's rule, we're going to have a kind of annoying numerator to take the derivative of, but the denominator won't be so bad, which is nice. And we know that the denominator is not going to be 0, so we won't have to do this again. So we're going to have a 2 in the denominator because the derivative of 2x is 2. And then negative tangent of sine x times cosine x is going to be a product rule. So it'll be negative tangent of sine x times the derivative of cosine, which is negative sine x. And then we will add to that the cosine x times the derivative of the negative tangent of sine x. Well, that's negative tangent u, so that'll be negative secant squared of u. And then we'll multiply that by the derivative of the sine of x, which is just cosine of x. So we got kind of a mess here to evaluate, but let's see what happens when we do it. The sine of 0 right here is just going to be 0. So all of this is just going to end up being 0. And then over here, the cosine of 0 is 1, right? So that's going to be 1. And then the sine of 0 here is going to be 0. So we want the negative secant squared of 0 times the cosine of 0. Cosine of 0 is again just 1. And secant of 0 is also just 1, right? So really what we've got in here is we've got 1 times negative 1 times 1, right? Because we have that negative sign out in front. All over 2, which just gives us negative 1/2. Right, just a couple more problems. I think we have 3 more problems to go here. So we've got the limit as x approaches 0 of 1 minus cosine 2x over 1 minus cosine 7x. If we do a limit as x approaches 0 of 1 minus cosine 2x, we end up with 1 minus the cosine of 0, which is just 1 minus 1. And the same happens for 1 minus cosine of 7x. We still get 1 minus the cosine of 0, which is 1 minus 1, or 0. So we will take L'Hopital's rule here and take our derivative of both the top and the bottom, giving us a limit as x approaches 0. The 1s will go away, so really it's just the derivative of negative cosine 2x. And since the derivative of cosine is negative sign, that negative is going to go away. So we just end up using the chain rule to get 2 sine 2x, and very similarly in the denominator to get 7 sine 7x. Immediately we should recognize that that's going to be 0 over 0, that the limit as x approaches 0 of 2 sine 2x is 0, and that the limit as x approaches 0 of 7 sine 7x is also 0, which gives us a second application of L'Hopital's rule, or the limit as x approaches 0 of, now it's going to be 4 cosine 2x over 49 cosine of 7x, which is just 4 cosine 0 over 49 cosine 0. Well, the cosine of 0 in both instances there, of course, is just 1. So we end up with 4 over 49. All right, our second to last one here. We're looking at a fairly complicated function there, e to the 2 plus x minus sine x minus e squared all over x. So we'll start off just by checking the limit as x approaches 0 of this. We have e squared, e to the 2 plus x minus sine x minus e squared, which gives us e squared minus 0 minus e squared, which is, of course, 0. And in the denominator, we have the limit as x approaches 0 of x, which is, of course, just 0. So we'll use L'Hopital's rule. Started to write limit, so we have a lowercase little l there. L'Hopital's rule gives us a limit as x approaches 0 of the derivative of e to the 2 plus x is just e to the 2 plus x, right? It's e to the u times the derivative of u. Well, the derivative of 2 plus x is 1, so there's nothing to multiply by except 1. Derivative of the minus sine should become a minus cosine x. The derivative of the minus e squared is not minus 2e because, remember, e is a constant. So e squared is a constant, so its derivative is 0. And in the denominator, we just have a 1, which we don't really need to write, but we'll keep it there for now. Evaluate this when x is approaching 0, right? When x is approaching 0, we get e squared, or e to the 2 plus x, minus the cosine of 0. And again, we don't really need that over 1, so we won't put it. And cosine of 0 is just 1, so we get e squared minus 1. All right, here is our last problem for this assignment. So we've got the limit as x approaches 3 of root 3x minus 3. Well, the square root of 3 times 3 is 3, and 3 minus 3 is 0. And we have a limit as x approaches 3 of root 2x minus 4 minus root 2. Well, 2 times 3 is 6, and 6 minus 4 is 2. So this is root 2 minus root 2, which is 0. So we can apply L'Hopital's rule. Using L'Hopital's rule, this becomes a limit as x approaches infinity of the derivative of root 3x, which is 1 over 2 root 3x, times the derivative of 3x, which is 3. And then we take the derivative of the minus 3 that's after that in the numerator, that's just 0. And then in the denominator, it's 1 over 2 root 2x minus 4 times the derivative of 2x minus 4, which is just 2. Okay? and then the derivative of the minus root 2 just goes away. We can, I think, cancel out these 2's here, right? So we just have 1 over root 2x minus 4. And then we can rewrite this, simplify it a little bit. Not sure why I wrote infinity here. Let's change that back to the 3 that we're doing. The limit as x approaches 3. And we're going to have 3 times root 2x minus 4 in the numerator over a 2 root 3x in the denominator, right? Because, I mean, that's, if you multiply by the reciprocal there, that root 2x minus 4 is going to go all the way up to the top. So now as we evaluate that, we've got 3 times the square root of 2 times 3, which is 6, minus 4, over 2 times the square root of 9. Well, the square root of 9 is 3, so those will cancel, and we just get root 2 over 2. And that is our final answer, and that is the end of our walkthrough for L'Hopital's rule. Just please remember, whenever you want to use L'Hopital's rule, that you always check that the numerator and the denominator make it indeterminate, that it's 0 over 0 or infinity over infinity. If it doesn't, you're going to end up getting the problem wrong. And also, just remember that sometimes L'Hopital's rule is not the easiest method, and sometimes it doesn't end up working. So you can't just forget all of our old rules for limits. Right? It's a great tool, but it is not the only thing you should be using when you have an indeterminate limit. And that's it.